In this video, we look at the mapping properties of analytic functions. We'll quickly have a look at examples of analytic functions. We'll look at the definition and examples of bilinear transformations. We will look at the definition and example of conformal maps. And finally, we come to the mapping properties of bilinear transformations. Okay. So polynomials are one of the most basic examples of analytic functions. So an example is given over here. Trigonometric functions like the sine function, the cosine function, the tan function in their respective domains, of course, are analytic functions. The exponentials like e raised to z, 2 raised to z are analytic functions. The rational functions, which are actually the quotients of polynomials, we have seen a theorem in the earlier videos that quotient of analytic functions are analytic functions, and therefore this is a special case of that theorem. Convergent power series in Z, these are analytic functions. In fact, there's a classification of analytic functions which says that any convergent power series in Z is analytic in its radius of convergence. Let's come to point number 2. Point number 2 is about bilinear transformations. So what are bilinear transformations? These are actually a special class of analytic functions. This is the definition. So az plus b upon cz plus d. So what is one looking at? One is looking at polynomials of degree 1 divided by another polynomial of degree 1. So one has to be careful with the denominator, and that is the reason that minus d over c is omitted from c to get the correct domain. So these functions which are bilinear transformations are also referred to by another name, linear fractional transformations. If AD minus BC, if the coefficients satisfy this property, that if AD minus BC is not 0, the collection of such functions forms a group, the group of Mobius transformations. So people who understand the language of groups, for them this is an example of a group. It's an infinite group, of course. Some examples of bilinear transformations. So here I've mentioned two very simple examples, f of z equal to 2z plus 1 upon z minus 1. So looking at the denominator, one has to skip this value 1. So this function becomes well defined. Similarly, in this particular example, iz plus 1 upon z plus I plus 1, one has to take care to omit the negative of this number from the domain. Conformal maps. So to understand conformal maps, let us look at this diagram. So in this diagram, I have a curve C1, I have another curve C2, and I look at the angle between the two curves. So how does one define angle between two curves? So of course you have to look at the point of intersection. The angle is a local concept, and therefore if you call P to be the point of intersection, then the angle between the curves is actually the angle between the tangents to the curve at that particular point. So in this diagram, T1 is a tangent to the curve C1 at P. T2 is the tangent to the curve C2 at P. Okay. And now what we do is we look at a map. So f is a complex function acting on this complex plane, certain domain of the complex plane, let's say. So this function will take the curve C1 to another curve in the W plane. We call that as C1 dash. So C1 dash is the image of C1. Similarly, C2 dash. C2 dash is the image of C2 in the W plane. P dash is the image of P. There will be some angle theta dash between the two curves C1 dash and C2 dash. So what is the angle between C1 dash and C2 dash? It is the angle between the tangents at P dash, between the angle between the tangents at P dash of the to these two curves C1 dash and C2 dash. Now it is not necessary that these two angles must be same, but if f is an analytic map, then these two angles will be same, provided an additional condition is also satisfied. So what is that additional condition? That additional condition is that the derivative of f at this particular point should not be equal to 0. Okay, so such maps will be called as conformal maps. In short, we say that angle preserving maps are conformal maps. That is what has been described in these notes over here. So we take a region and then we take a function. We say that a function f is conformal at z0 if f preserves angles at z0. And now we understand what does it mean that a certain function preserves angles. Okay, let us have a look at some examples. I have already given you a clue. So a lot of conformal maps come from analytic functions. So if f is defined on a region R and it is analytic at z0, if f dash z0 is not 0, then f is conformal. This is a theorem, I just mentioned that. If you want a concrete example, you can take this. F of z equal to z square minus 4z. The derivative of f is 2z minus 4. That's easy. And the derivative will not be 0 provided z is not equal to 2. Okay. So this map is conformal at all points except z equal to 2. Okay, so from a function being conformal at a point, we generalize it to the function or the map being conformal in or on a region R. So if f is conformal at all points of R, then it is said to be conformal in the region R. Okay. Here we look at another set of examples. So these are the bilinear transformations. Okay, and we look at the group of Mobius transformations, functions of this kind where AD minus BC is not equal to 0. Let us differentiate this. So I have worked out the derivative over here, and the derivative turns out to be this quantity, AD minus BC upon CZ plus D whole square. Now obviously this is not 0 because the numerator is not 0 by this particular condition. So F is analytic, which is already known to us at all points except minus d by c. And because of this calculation, f dash z is not equal to 0 anywhere in the domain, right? So such a map preserves angles. Such a map is conformal. Let's come to the mapping properties. So we look at the mapping properties of bilinear transformations. We just noted that bilinear transformations of this kind, where AD minus BC is not equal to 0, are conformal. So this is just a repetition of what I just said some time ago. F has at most 2 fixed points. What is a fixed point? A point which is taken to itself under the map is called as a fixed point. So if z equal to z0 is a fixed point, then the map takes the point to itself. Okay, example. So if we look at fz equal to 2z plus 1, then z equal to minus 1 is a fixed point. Why? So if you put z equal to minus 1 in this, so you get 2 times minus 1, which is minus 2, plus 1, which is minus 1. So the point minus 1 is taken to itself. So z equal to minus 1 is a fixed point. Let us have a look at another property of mapping property of bilinear transformations. So suppose z1, z2 and z3 are 3 distinct points in the z-plane, and w1, w2, w3 are another 3 distinct points in the w-plane. Then this is a theorem which says that there is a unique bilinear transformation which maps this collection of points to this collection of points. So if you have a diagram, so suppose we have, so this is the z-plane, and I have z1, z2 and z3. These are the 3 points in the z-plane. And similarly, you take the w-plane and you take 3 arbitrary points, w1, w2 and w3. Okay? Then what this theorem is saying, what this statement is saying, is that there is a unique bilinear transformation. There is one and only one bilinear transformation which takes z1 to w1, z2 to w2 and z3 to w3. So take 3 distinct points here in this plane, 3 distinct points there in that plane. There will be a unique map which takes z1, z2, z3 respectively to w1, w2 and w3. This is a very useful theorem in and using this theorem you can actually work out that bilinear transformation. So we are going to have a look at an example of that kind. Okay, so in this example, this is an illustration. I take my z1 to be I, z2 equal to 0, z3 equal to 1, and these are mapped into the w plane to the points 1, minus I and minus 1. So what is that bilinear transformation? The a bilinear transformation exists which does this mapping is guaranteed by this theorem. Okay. So I'm going to now find that bilinear transformation. So let me assume that the required bilinear transformation looks like this. It looks like az plus b upon cz plus d, ad minus bc not equal to 0. Okay. Now c and d both cannot be 0, because if both of them are 0, this condition is not satisfied. Okay. So let me take the case d not equal to 0. Okay. Now if d happens to be equal to 0, what happens? So if d is equal to 0, this is simply of the form alpha plus beta by z. All right. And then we can give a different argument. Okay. First, let us just proceed with this assumption. So suppose d is not equal to 0. Okay, so what I'm doing here is looking at the case when d is equal to 0. Fine. So when d is equal to 0, then w is equal to a dash plus b dash by z. Okay, where obviously a dash will be a upon c and b dash will be b upon c, right? So that comes from here. That's very easy. So what we do is we apply the map. Applying the map means what? So take I, z1 equal to I. So if you substitute z1 as I in on the right hand side, then the value is 1. So 1 is equal to, now this map has reduced to this, so 1 is equal to a dash plus b dash upon I. That's the mapping. Similarly, as 0 is mapped to minus I, alright, so put z equal to 0 in this, and the image value minus I, so you get this. Okay, now b dash divided by 0 is infinity, so that gives rise to a problem. So this is absurd. Okay, so we cannot so this is at sort of a valid invalid assumption. Therefore d should not be equal to 0. D cannot be equal to 0, and if d is not equal to 0, I go back to this equation and divide the numerator and denominator by d. So what I get is a upon dz plus b upon d. Similarly, denominator c upon d z plus 1. Okay, and I rename these constants as a, b, c. Okay. Okay. Now we do the same thing as we had done earlier when d was equal to 0. So we apply the mapping now. I going to 1, 0 going to minus I, and 1 going to minus 1. This will give me a set of equations. So what we get is, so with the first one, I get this equation. With the second one, I get this equation. With the third one, I get this equation. Okay. Okay, now the second equation immediately gives me that b is minus I, and the remaining two equations give me, after simplification, I get these two equations, simultaneous equations, in the two unknowns a and c. So what I'm doing now is solving for a and c. Okay, so once I divide by I on both the sides, this equation becomes this. Okay, and now the calculation becomes easier. So when I add these two equations, I get 2a equal to, so this is 0. 2a equal to 0 gives me a equal to 0. And once a is equal to 0, I get the value of c as this from this equation. Okay, so I have the values of a, b, and c. A is 0, b is minus I, and c is equal to minus 1 plus I. So f of z is equal to this. And this is the required bilinear transformation. Okay. Okay, this example can be done in a different way, and that is using the idea of cross ratios. That is the next thing. So what are cross ratios? So if I write down 4 complex numbers z1, z2, z3, z4, okay, look at these lines. So I take z1, z3 and z2 and z4, cross them. And I take z2, z3 and z1 and z4. I form a ratio. So the up arrows form the numerator. So z1 minus z3 is the first number. I multiply it by the difference of z2 and z4. And in the denominator, I take z1, z4, the difference between these two, and difference between z2 and z3. This is called as a cross ratio. And it happens to be a very interesting object. Okay. Okay, the theorem is the following, that if w equal to f of z is a bilinear transformation, ad minus bc not equal to 0, okay, and if there is a mapping property like this, that zi goes to wi, that means f of z1 is w1, f of z2 is w2, f of z3 is w3, then this map can be obtained through this cross ratio. Okay. All right, let us look at an example. So I take the same set of three points, I, 0 and 1. So Z1 is I, Z2 is 0, Z3 is 1. And it is mapped to 1 minus I and minus 1. Okay. So just apply this mapping to this, okay, and you'll, after some simplification, you get an equation like this. All right, so we just solve for W from this equation by using, so here I've used component and dividend. Do that, simplify it, and after the simplification, so this is the simplification, and we get W equal to this. You can check that the answer is exactly the same as we had obtained through the previous method. So that's all in this video.